So we're going to focus a bit more now on this last part of the slides where we're looking at what's happening at a carbon called the anomeric carbon. So a sugar anomer is any sugar that differs only about the anomeric carbon, which is carbon number 1 in an aldose or carbon number 2 in a ketose. And so the anomeric carbon in the linear structure would have been the carbonyl carbon. And we can see that on the bottom because I've shown us both the linear and the cyclic versions. So glucose is an aldose, which means it has an aldehyde. We count that carbon as carbon number 1, so it would be the anomeric carbon, but you can see if we keep going, we just keep numbering the carbons, 1, 2, 3, 4, 5, 6. So when we go from the linear to the cyclic form of glucose, carbon number 1 is still the anomeric carbon. It's just harder to tell because we no longer have that carbonyl. But if we're comparing linear and cyclic, we can tell, okay, carbon 1 has the carbonyl, carbon 1 must be the anomeric carbon. Same goes for ketoses. If the ketone is at carbon number 2, carbon number 2 is the anomeric carbon. And so we distinguish anomers because the geometry about the anomeric carbon matters. An anomeric carbon can have a bond that is either alpha or beta. In an alpha anomer, the OH substituent is on the opposite side compared to the large, bulky CH2OH. So you see this OH is pointing down. It is opposite to this bulky CH2OH. It is alpha, anti-opposite. However, beta has that OH off of the anomeric carbon going in the same direction as the CH2OH. So beta is the same. Before we dive a little bit deeper into this, folks, I do want to just briefly mention that sugars undergo more reactions than what I am showing you here. You can reduce sugars for a variety of reasons that are important to physiology. For example, deoxyribose. You can add amines, not just hydroxyl groups, to sugars to make amino sugars, and these are an important part of both protein and lipids that perform covalent bonds with sugars. Back to that anomeric carbon. So the anomeric carbon is of such focus because it is performing the glycosidic bond. The glycosidic bond links the anomeric carbon to any non-hydrogen substituent. In the previous slide, it was a hydroxyl group, OH, but it could be anything. It could be OCH3, it could be O, and then an entirely new sugar molecule. This bond is very stable and generally will not hydrolyze in water. We'll need like an enzyme to cleave the bond. For a little bit of additional practice, folks, let's look at this alpha and beta glucose in the bottom and determine if they truly are alpha and beta. Let's start with the alpha. We'll find the anomeric carbon at carbon 1, and we'll see that the OCH3 is pointing down. This is anti or opposite to the CH2OH, so yes, this is an alpha. What about the beta? Is it on the same side? Well, yes, that OCH3 is pointing up, same way as the CH2OH, so yes, that is a beta glycosidic bond. Now, as I mentioned, this glycosidic bond can be formed not just to small substituents such as OH or OCH3, but also just a whole nother sugar. And I'll give you two examples of this. The first is lactose. This is a simple disaccharide found in milk. If you're able to drink cow's milk, you must be lactase persistent, so your body makes the enzyme lactase that's able to digest this bond. If you are lactose intolerant, sadly, you do not make that enzyme anymore. Lactose has a very long name, shown here, but there are two aspects of this name that I want us to focus in on. The first is this beta, and then the 1,2,4 designation. So the first beta references the glycosidic bond of the first sugar, galactose. So let's first convince ourselves that this is truly a beta glycosidic bond. Galactose is an aldose, so carbon 1 is the anomeric carbon. Is its glycosidic bond beta? Well, the bond is drawn like this, so it's kind of wonky. But you can assume this bond means the bond is going up from this carbon and is going down from that carbon. If this bond is going up, then yes, this galactose is in the beta configuration since it is on the same side as the bulky CH2OH substituent. What now does the 1,2,4 mean? The 1,2,4 tells us that the bond is going from the anomeric carbon, carbon number 1, to carbon number 4 on the second sugar unit. So that's what 1,2,4 means. Let's do one more example. Here we have sucrose, which is a common sugar found in plants. So if you ate any fruit today, you just ate some sucrose. This is a slightly more challenging example. Why? You see we have an alpha, you see we have a 1 to 2, and we also have a beta. So what's going on here, folks? What's going on here is that we are working with glucose, which is an aldose, and fructose, which is a ketose. So we have two different anomeric carbons to take account. Let's start with glucoses. So glucose, we have this alpha to deal with. Let's see if it's alpha. Now this bond, again, is this weird kind of squiggly bond that looks like this, but we'll understand that to mean that these bonds are coming down. So at the anomeric carbon of glucose, carbon number 1, it is pointing down, which is anti or opposite to the bulky substituent. So yes, that is alpha. Great. What about this 1 to 2 business? We have a bond from the anomeric carbon of glucose, carbon 1, to carbon number 2 of fructose. So that is the 1 to 2 designation. Finally, what's going on with this additional beta that we have to deal with here? Well, since fructose is a ketose, this means that carbon number 2 is its anomeric carbon. So we have this odd arrangement where we have a glycosidic bond from glucose's anomeric carbon to fructose's anomeric carbon. So we must also give the designation of fructose's anomeric carbon. Now the glycosidic bond on fructose is pointing down, as is its bulky substituent opposite. So yes, that is beta, and we are all good there. Last up, folks, we'll talk about some polysaccharides and their use, and we'll wrap things up.